Hello and welcome to this video. My name is Owen Chalmier and I'm going to discuss a method of condition monitoring for rotating machines using supervised machine learning. All of the content in this video can be seen in my paper titled Wear State Estimation of Rolling Element Bearings using Support Vector Machines, which you can access via the link below in the description. This work was presented and published at the 15th IEEE International Conference of Signal Processing hosted in Beijing. Here's a quick high-level look at what's in store for this video. First, I'll give an overview of the area of condition monitoring, outline the proposed methods, and finally discuss the result obtained on a real dataset. Electric machines are a key component for major industries such as manufacturing, energy, and transport sectors. It is vital that these machines are operating at optimal conditions. Abrupt equipment failure in systems such as aircraft, electrified vehicles, renewable energy systems can have serious health and safety implications. Minimizing failures and being able to predict mechanical fault modes allows for repairs to be completed during controlled and scheduled maintenance windows. This significantly reduces the high costs associated with equipment failures, delays, and downtime, as well as the severe mitigation of reliability concerns regarding health and safety. There are three major maintenance approaches to consider, the first being reactive, when machines are simply run to the point of failure before any maintenance action is initiated. The second is preventive, which involves scheduling regular checks on the performance of a machine to replace components before they reach the stage of severe degradation. This option improves upon the previous by eliminating the occurrence of catastrophic failures, but the main drawback is determining the most optimal time to perform the scheduled maintenance in order to get the maximum usable life from the component. A better option is a prognostic condition monitoring approach, involving an online monitoring scheme to give an accurate health state indication of when to perform targeted maintenance actions like repairs or part replacements. Generally, a condition-based monitoring system will incorporate 7 layers, which include sensors, signal processing, fault detection, health assessment, prognostic, decision support, and finally a presentation layer. Data acquired from various sensor types can be used to calculate the time left before failure occurs. This time is also known as the remaining useful life of a component. Knowing this time means the health state of a machine can be predicted so that suitable maintenance can be carried out at the optimal time. Bearing failure is responsible for the breakdown of up to 75% of all low voltage motors and generators. It is one of the most common types of machine fault and is also recorded to be responsible for up to 40% of all machine failure. Popular methods of condition monitoring machine failures include bearing vibration, acoustic noise, stator current, thermal imaging, and multiple sensor fusion. Vibration analysis was found to be the most favorable approach due to the non-invasive, non-destructive nature of acquiring online data samples. Signals are recorded using accelerometers mounted to the machines and can be used to gather data without the need to disassemble or power down operating equipment. The challenge with using these signals is that they are non-stationary, extremely small in amplitude, and susceptible to high levels of noise from the environment. Because of this, we need to combine signal processing techniques with machine learning methods. Machine learning is a subset of artificial intelligence and can be used to identify existing trends, patterns, and relationships in large data structures, which enables us to make intelligent decisions regarding the health state of a machine. This degradation process from unage to failure typically takes many years to occur under real-world conditions, so it's pretty much unfeasible in practice to achieve. To build and test prediction models, we use data created by carrying out accelerated aging experiments. These experiments are performed under controlled lab conditions and involve increasing the loads and operating speeds or elevating the temperature and humidity. The methods and approaches in this paper have been designed and tested using the 2012 IEEE PHM challenge produced by the Femto Institute in France. For this particular dataset, bearing signals are acquired using 2 orthogonally placed accelerometers fixed to the horizontal and vertical axis of the bearing's external race. 7 bearings were run to failure at operating speeds of 800 RPM and a load of 4,000 newtons was applied. Signals were recorded every 10 seconds at a sampling frequency of 25.6 kHz until failure was detected with the signal amplitude surpassing the value of 20 G. Machine learning algorithms are heavily reliant on quality of the data being used to train, validate, and test prediction models. This paper explores two different methods of extracting useful time frequency features from the quasi-stationary discrete time sensor signals. The first method, which performs significantly well, is the short-time Fourier transform to obtain the spectral components of the signal. The transform involves calculating the windowed DFT of time samples, with each window overlapping the previous by a factor of 75%. The average value of these complex features is calculated for each time sample, which produces a spectral feature vector consisting of 512 points. These points are separated at intervals of 25 Hz and represent the spectral amplitudes over a range of 0 to Nyquist frequency of 12.8 kHz. The second method of time frequency translation used is the signal envelope extraction. Sixth order FIR Butterworth filters are used to reduce the signal SNR. The signal is then demodulated by taking the absolute value of the signal points and applying the Hilbert transform to form the complex analytic signal. Taking the magnitude values of these complex analytic signals gives the signal envelopes. The next step is to reduce the dimensionality from 512 down to 25 spectral features. The motive being to extract the most useful features to train the prediction models. Reducing the number of features simplifies the complexity of the calculations so that more accurate estimations can be made. This was achieved using a filter band approach of both linear and non-linear sized bands. The linear bands consist of 25 equidistantly spaced bands applied to 512 spectral features. The nonlinear approach uses a 1/3 octave band filter. This filter places a higher emphasis on the lower end of the frequency spectrum by having more frequent bands on the smaller frequencies. These bands then increase towards the Nyquist frequency. The signals were divided into 5 wear states to classify the health stage of the bearing. We investigated different approaches to assign these 5 classes. The first is a linear approach consisting of equidistant classes, each representing 20% of the bearing's lifetime. The second is a nonlinear approach, where class 1 represents the entire first 50% of the lifetime, class 2 represents the next 25, and so on. Analyzing the vibration signals in the time domain shows that the latter stages of the bearing's lifetime should be given a much greater emphasis, as the signal amplitudes seem to increase at a much faster rate here. All 7 bearing test cases were used in a round-robin formation, where 6 bearing signals were used to train the machine learning algorithm, and the 7th was used for testing. Once remaining useful life estimations had been obtained for each of these out-of-sample test signals, the bearing was added back into the training pool, and the next sequential bearing was transferred to the testing pool. The model was retrained, and this was repeated for all 7 test cases. This framework was incorporated to minimize overfitting by using only out-of-sample test cases to perform classification. The final step is the classification stage. We use a support vector machine, or SVM framework, testing 6 different kernel functions. The training data is mapped to a higher dimensional feature space to find the optimal separator between classes. This transformation to higher dimensional feature space is called kernelling, and the separating feature is known as the hyperplane. Target instances are classified by their position in the feature space relative to the separating hyperplanes. The performance of each approach was analyzed by taking the Jacob index and multiplying by a factor of 100 to get the percentage accuracy value. This Jacob index value is simply just the number of correctly classified samples divided by the number of total test samples. The scores in the table are the mean scores for all test samples in the 7 bearing test cases. The highest results for both the linear and non-linearly spaced classes was achieved by the 1/3 octave band feature set in the horizontally recorded signals using a medium Gaussian SVM kernel function. The highest overall accuracy score of this study of 67.6% is really impressive considering this is a multi-class problem with over 14,500 individual time samples to be classified. The results show that the 1/3 octave band feature performs significantly better than both the 512 features and the linear band features. This paper proposed a novel feature selection approach, the 1/3 octave band scale, to select features. This puts more emphasis on the lower portion of the frequency spectrum, where more meaningful degradation information can be acquired. Nonlinear class boundaries are found to be superior instead of linearly spaced classes. The degradation starts with the gradual incremental changes, while towards the latter stage it suddenly reaches a point of rapid change, culminating in an avalanche-like pattern. The high level of results using the signal envelope features and SVM approach for classification proves that the simple and versatile traditional machine learning methods are sufficient, and that we don't necessarily need complex tuning to achieve high results for this application. The best approach to apply was found to be the medium Gaussian SVM kernel function to achieve the highest classification accuracy. This framework could be updated online with very little processing steps, as new instances with known classes become available. The main drawback with the supervised machine learning method is that they are relying heavily on the quality of the training data samples. In this case, we are relying on the ground truth wear states being distinguishable and effectively spaced to ensure that the classifier can perform accurately and precisely. This research provides a robust framework for industry developers to implement a sophisticated online prognostic condition monitoring system. These vibration signals can be processed locally on electronics hardware or be ported to the cloud for large-scale deployments to estimate the remaining useful lifetime of rotating machines. This is valuable for the automated scheduling of maintenance and replacing of parts to prevent costly downtime, or in many cases, health and safety incidents from occurring for mission-critical applications in the automotive, aircraft, and large industrial machine industries. The link to view this paper on ResearchGate is listed in the description below, and if you have any questions, please feel free to contact me through any of the platforms linked below. Thanks for bearing with me.